So yeah, like I said, your test 2 has been rescheduled to week 11, and I will be taking some additional lecture today just to compensate for the next week's lecture. So after the day 9's lecture is done, I will be starting off with the day 10 lecture. But this day 10 will not be included in your test. So it's only going to be from week 5 until week 9. Okay, so I hope that is clear. And I just started sharing a few of your marks. I haven't got around to everybody, so I'll slowly get around maybe before the end of class today. All right. So yeah, let's start off with the lecture. So today it's about references. So let's see what references are. So reference is basically an alias. So when we say an alias, it's like an additional name. It's like an additional name to a thing. All right. So it's like you have an alias name. So you have an additional name. That's exactly how it functions in programming. So whenever you create a reference, you must initialize it with a target. So for example, I have a, just change this to, yeah, so you can see where I'm talking. So now suppose I have an integer variable called inum, but I want it to be referred to by another name, say rnum. So what I need to do is I need to declare that this is a reference that is called rnum, which refers to the same variable inum. And for that, I'll be doing int ampersand. All right. So ampersand is the main point over here. This ampersand at the point of declaration tells the compiler that this is a reference. This is a reference to something else. And now since I'm creating a reference to the integer variable, I'll have to declare it as int ampersand or int reference. All right. So at the point of declaration, we'll need to specify which variable this has to refer to, or which variable this is an alias to. So the statement saying int ampersand rnum is equal to inum is very important, because if you just declare int ampersand rnum, then that is going to throw you an error, because the reference should be initialized at the point of declaration. All right. So you can try out int ampersand rnum and see what sort of error you get, and then you can understand why this is particularly important. All right. Even meaningfully, you wouldn't create a reference simply. A reference or an alias is to something that is already existing. Okay. So from that point on, the reference acts as an alternate name for the target which is inum over here. So I hope you're all clear with the basic declaration. The declaration that you have to take care of is the data type followed by ampersand and the name of your reference variable equal to the variable that you want to alias. All right. So I can't see any doubts at this point. So I'll just move on to the next slide. So yeah, you can see this example over here. So I have something called isumInt. I have an integer variable called isumInt, and I want to create a reference to that, or I want to create an alias name. So I'm just creating an alias name called rsumref, ref indicating that's a reference, r again indicating it's like a naming convention. So since I use I for the naming convention, there is in the same naming convention I would use r to refer to indicate that this is a reference variable. All right. Now, since I want this reference variable to actually refer to an integer variable, my declaration will be int ampersand. If I wanted the reference to be created to a character variable, it would be char ampersand. All right. So it is int ampersand r sum ref is equal to I sum int. And so if I do r sum ref is equal to 10. So remember r sum ref is a reference to the I sum int. So if I do r sum ref is equal to 10, and if I try to print out the value of the original integer name with using the original integer name, it is going to show me the new updated value that is 10. All right, because when I change a value in r sum ref, so I'm saying the alias variable, the alias variable now contains the value 10. So the alias variable is actually referring to variable. So obviously the integer value is going to be changed. So it's going to be updated from 20 to 10. So it's like saying you've got two names with you. You're called by two names. And if you have first maybe $20 with you, but then you lose those $20 and you have $10 instead. So whatever your name is, you have just $10 with you. All right. So yeah, think of references in that manner. So the main thing is to create a reference, you need the ampersand sign at the point of declaration. And we usually prefix it with R to indicate that it is a reference variable. Okay. So create meaningful names for the reference as well so that we understand which variable it is referring. Okay. So if I say int I sum int is equal to 20, int is allocated a memory location which contains the value 20. And if I create a reference to that I sum int, the R sum ref refers to the same I sum int. So whenever you do something to the R sum ref variable, actually editing the I sum int itself. So you're editing the same memory location. All right. So anybody has any doubt? I can see Lara's typing something. Okay, so I guess everybody's fine.
Just
Yeah.
quickly,
Okay.
why would you use a reference instead of a pointer?
Because a pointer is really cumbersome. So if you remember how we use pointers, we have to dereference it every time we want to access the value, correct? We'll have to do asterisk pointer each time. So since we are humans typing out the code, there might be a point where we miss out the asterisk sign, but still the compiler will not throw an error. So instead of saying asterisk pointer is equal to something, you might just say point ptr is equal to maybe 10. So in that case, what happens is the pointer um, changes the location it points to. It just points to another memory location whose address is like 10, and that is one of the crucial system addresses.
Can you use a reference like in a different class or a different function? If you're talking right now, I can't hear you.
Can you guys hear me now?
Yep.
Yes.
Sure
Yes.
can.
Okay, so I'll go live again. All right. Okay, is it okay now?
Yep.
Okay. All right, so I'll just repeat what I said earlier. Um, so the difference between a pointer and a reference is that a pointer is rather cumbersome because for a pointer you will need to keep dereferencing the pointer. So I hope you remember how to dereference. You will need to use an asterisk sign every time you try to dereference. So it wouldn't be as easy as just writing r sum ref is equal to 10. You would need to say asterisk ptr is equal to 10, asterisk another ptr2 is equal to 100 or something. So if at a point you miss out the asterisk sign, which is to indicate that you want to dereference the pointer, what happens is you're trying to change the address value that was pointed to by the pointer. So if you write ptr is equal to 10 by mistake, what you're saying is the PTR should actually point to an address location 10, and that might be one of the crucial system addresses. So since pointer makes you really powerful, you don't want to do something dangerous of that sort. So as you can see over here, this reference variable just behaves the same as any normal integer variable. You would never know this was a reference variable unless you go to the actual declaration. All right.
Right. So in case you got cut off earlier before I asked the second part of my question was, can you reference across functions?
Yes, you can, and that is one of the main applications of this. That's what I'll be discussing in the coming slides. All right. So, yeah. So I hope I can move forward now.
Yep.
Are you all okay? Yeah. All right. So in the coming slides, we'll just see the application of references, and that will make it more clear. All right. So I've already done this. So you can see how our sum ref refers to the same integer variable, which is the same memory location. Okay. So now if you try to access the address of a reference variable, how would you get the address of a reference variable? Just use the ampersand sign again. Remember, whenever you use the ampersand sign at the point of declaration, that means it is a reference. That means you're declaring a reference. But if you use the ampersand sign uh, otherwise, that is when it is not at the point of declaration, or when it is on the left-hand side of your statement, or when it is on the right-hand side of a statement, or when you want to print out, you say cout ampersand some variable. That is going to give you the address of that variable. So if you try to get the address of your target, that is the address of this rsum ref, for example, is going to return the address of the original integer. All right. So address of rsum ref will return the address of isum. So there's no way you could get the address of the reference, because whenever you call the reference variable, it's always going to point to the original integer variable. That is the original name of the variable. Okay. Because that's even not meaningful. The reason you create references is because you want to create an alias, and alias alias names are basically just additional names to your original name. All right. So can't see any doubts now. Okay, so this is just another example just to see how reference works. So suppose I declare an integer variable called I1. So I1 has some memory location in your memory. It will have some garbage value there. It is not going to be empty anytime. Now if I say declare a reference variable that points to I1. So say rsum ref is equal to I1. So this rsum ref refers to the, or is an alias name to the I1. And I'm saying I1 is equal to 5. So the garbage value, whatever garbage value was in there, is replaced by 5. And then there's another variable called I2, which is 8. And now what I'm saying is rsumref is equal to I2. What do you think happens in this case? When I say rsumref is equal to I2,
Does it try and change what an I1 is?
yes, that's what happens. So it tries to change the value that is there in I1, if that's what you said. All right. So what happens is this value that was 5. So you can see the value 5 in there changes to 8. And that's what happens. So when I say something like rsumref is equal to I2, do not assume that rsumref is now going to be an alias name to another variable called I2. That is never going to happen. All right. This statement rsumref is equal to I2 is the same as saying I1 is equal to I2 or I1 is equal to 8. Okay. So rsumref is like an alias name forever to I1. The alias name, this alias name is never going to be referring to any other variable other than I1. If you want a reference variable to I2, you will need to create a brand new one. All right. So the same as doing I1 is equal to I2. So I1 equal to I2 basically means taking the value of I2. Yep. So a few of you had given the right answers for that. Yep. All right. So any doubts with this example? Okay. So I'll just go forward. So one of the rules is the reference cannot be null. So never attempt something like, say, a pointer which is initialized to 0. If you remember, any pointer that's declared has to be initialized to 0 so that it does not point to any random memory location and try to edit that. So if I try to declare a reference variable using the declaration in reference y is equal to asterisk x. So what does asterisk x mean? This is actually dereferencing the pointer variable. So this reference is an alias name to the to the to the mem to the memory location that is pointed to by x. Okay, so this reference is not a reference to the pointer. It is a reference to the memory location that is pointed to by the pointer. So if you try to do something like this, it basically means it is pointing to a null value. This doesn't throw you an error, remember, but then it is going to be an invalid memory access. So you might assume actually doing something in you're actually doing some changes to the to some memory location using y, but this is not pointing to a valid memory access memory location, and that's why it might create problems in your code. So just take care of that whenever you declare references. All right, because this is something you will need to do. You will need to check on your own to make sure your reference is not pointing to an invalid memory location, because this particular statement is not going to throw you an error. All right. So the differences between references and pointers. So if you see over here, this is the difference in the declarations. So the pointer, to declare a pointer, you need an int asterisk declaration. To declare a reference, you need an int ampersand declaration. And a pointer does not need to be initialized at the point of declaration. So if you haven't decided what the pointer should point to, you can just say the pointer is equal to 0 so that it doesn't become a dangling pointer, or it's not a wild pointer. And then later, when you have decided what the pointer should point to, you can just say that pointer that is like p_sum pointer is equal to address of variable that you want to point to, or any other data type, the address of any other data type. Whereas in the case of references, a reference should be initialized at the point of declaration. If you don't do that, it's going to throw you an error. All right. So yeah, basically pointers are variables that hold the address of another variable, whereas a references are for the purpose of creating aliases to another variable. All right. So one of the main reasons we go for references is to pass arguments to a function. So far we have seen passing arguments to a function by value. By value basically indicates that whenever you pass the required arguments to a function in order to perform a certain function, in order to perform the required operation of the function, the values itself do not get changed because only a copy of the value gets passed on to the function. All right. If you don't remember all these concepts, please go back, please revise all of them because anyway you would be requiring them for the test. All right. And the second type we learned was passing values by pointers. So when you pass values by pointers, um, what happens is you will be able to edit the values that is being passed as well. All right. So we'll now see the three different types, that is passing values by value, which doesn't make any change to the arguments, passing values by pointers, and passing value by references. So these are all slightly different syntax, but it gives you but these two cases, that is the pointers and references, gives you a similar result. All right. So this is a normal pass by value method. So in the pass by value, you can see what we do. So suppose in the main function, I've got an ix and iy, which I want to pass to a swap function. So this ix and iy are passed to the swap function. All right. And since you can see no pointer signs, no ampersand to indicate a reference, this is a pass by value. All right, because there's nothing special about this. So this is the default method. So if you don't have anything there, that's going to be a pass by value. A pass by value basically means there's a copy that is in the scope of the main function. I mean, there is one copy in the scope of the main function, and there's another copy in the scope of the swap function. Okay, so I've got new locations created for ix and iy with the same values, that is 3 and 5. So what happens after this function is created? So this swap function is designed so that these two values get interchanged. So here I have got a temp variable. Temp is equal to ix. So temp stores the value of, and then I say ix is equal to iy. So ix gets the value of iy, that is ix becomes 5. Iy is equal to itemp. So iy gets the value that was an itemp. Itemp had the value 3. So this would be 3. All right. So the values would be interchanged in this manner after this function gets executed. But what happens after this function completes its execution? That is, it encounters the curly braces. Values gets, or these memory locations gets destroyed, or these values get. All right. So do you see any change in the original ix and iy? No. Assume that calling the swap function using these values would swap the two values, then you're wrong there because the values remain. You could try to return something from the function, but remember you can only return one value from a function. If there are multiple values that you want to change, if there are multiple values that require to be changed, then you will need to do something to the passed arguments because the return value only allows you to return one. All right, so that is a pass by value method. So any doubts at this point? Okay, so Hamish, I'll be giving you your marks one by one. So that I'll be messaging you uh, on your personal, I mean on Discord. All right. So I've not done it yet. I'm messaging all of you through Discord. All right. So if there are no doubts at this point, shall I move forward? That's okay. All right. And the second method is passing values using pointers. So you can see the difference here. In the previous swap function, it was just a normal, it was just normal integer variables as arguments. There's an integer asterisk pix and integer asterisk piy, which clearly shows that these are pointers. All right, because at the point of declaration, if you've got int asterisk, that indicates that it's a pointer. But a pointer also requires that you pass address of variables. So you can see at the point of call, we are passing address of ix and address of iy. And that is why the pix holds the address of ix and piy holds the address of iy. So you're passing I address of ix to the first one, that is pix, address of iy to the second one, that is piy. This method of passing values. So this is passing using pointers. All right. Happens when this function gets executed, that is a swap function. So it's the same logic. The only difference is since we're dealing with pointers over here, we'll need to dereference at each point. So you will need to say int itemp is equal to asterisk pix is equal to asterisk piy, and asterisk piy is equal to item. So do not forget to dereference every time you use pointers. And that is the only difference that the code has with the previous one. Okay, so after this code gets executed, what happens? The values that is the memory locations that is pointed to by these pointers have their values interchanged. So 3, 5 becomes 5. Now, after execution of this function, after the function completes its execution, what happens? The pix and piy gets destroyed because the scope was only within this function, but these values remain unchanged. All right. So the interchange values 5 and 3 does reflect in the main function too. And there you have your swap function successfully um, successfully implemented and retrieved. All right. So if you want to make changes to multiple variables, go for using pointers, or the other method is using references. So I hope this is clear. I can see no doubts at this point. So moving on to the next one, let's see what the difference is with using references. So using references, the first thing you need to do is change the declaration type to the function prototype. So instead of int asterisk like the previous slide, you would have an int reference or int ampersand. All right, so I have int ampersand rix and int ampersand r. The rest is the same, okay? But you can see how it is different in the function over here. Rather than like in the previous slide, where I had asterisk pix, asterisk piy everywhere for to the memory location point to the by the pointers, I had to do a dereferencing, asterisk here, and each and every line wherever I use the pointers. But in this case, all I'm doing is I'm just accessing the reference variable as it is, as though it was a normal variable. So this function is similar to your first case where you were doing a pass by value. The advantage of a pass by value is it's easier to code because you don't need to dereference every time. And the same advantage holds in the case of references too, because reference acts like a normal variable. So you just need to use the variable name and you don't need to do any dereferencing there. Okay. So here I am saying int itemp is equal to rix, and the logic remains the same. What happens when this function gets executed? Rix refers to the same memory location, riy refers to the same memory location as ix and iy. So when I function, the values get interchanged. That is, one gets 5, the other one gets 3. And now after execution of this function, oops, after execution of this function, the rix and riy gets destroyed, but the 5 and 3 remain. Okay, so my purpose is achieved. The swap function does interchange the two values, but it's also easier to implement it using references rather than using pointers. So in this case, it is advantageous to go for references rather than pointers. In some cases, you might still need to go for pointers, but wherever possible, try to make use of references so that you do not make any unwanted change to the or unwanted problems in your code by forgetting to dereference the pointer at a point. So Neris is having a method with reference parameters a valid overload. Uh, for overloading a method, I guess most of you do not know about overloading, so do not get confused at this point. Those who can understand, okay, fine. The others, don't worry about it. So it's having a method with reference parameters a valid overload. Uh, no, that is going to be an invalid one, Neris, because when you overload a function, when I pass integer variables, suppose you have one function with no references, the other function with just normal, with just a pass by value method. And when I make a function call passing the two variables, then the compiler doesn't know which one to select, and that's when it's going to give you an ambiguity error. All right. So yeah, references is not a valid overload. Overloading is having different arguments. Yes, Michelle. Yeah, it's having different arguments, so that differs in terms of the number of arguments or the type of arguments. Okay, so let's just leave all that now for now. That is like totally at the end of almost at the end of the course. All right. So moving on to the next one in this case. So yeah, we're almost done with references. So in the case of references, it's easier to maintain and read than with pointers. All right. And you are allowed to declare constant references. So why would you declare a constant reference? You would declare it if you wanted the reference to point to an actual value. Okay, so far what we did was our references was always an alias name to another existing variable, to another variable that we had created. But suppose you want to create a reference to some constant value, like one or say some string value, then you will need to declare a const int reference. There is no other way to do it. So if you were to do something like int reference value ref is equal to 1, this is going to throw you an error because 1 is a constant value. A constant value cannot be referenced by a normal integer ampersand. You will need a reference. So moving on. So the one of the main advantages, you can return multiple values from the function like we have seen in the swap function. So using pass by reference allows the function to change the original variables. So if you want multiple changes, multiple values to be updated from a function, either use passing by pointers or use passing by references. The advantage of references over pointers is that references do not need to be dereferenced every time like pointers. All right, references can be used by normal variables. The only point there's a difference is at the point of declaration. Okay, so in the function prototype, you would be using an int ampersand to indicate that this is a reference. In all other cases, in all other usages later on, you would just use it like a normal variable. But in the case of pointers, you have to dereference. You have to use the asterisk sign every time, or else you would be changing the memory location that was pointed by the pointer itself. And this is not going to throw you an error at any point. Remember that. This is totally your responsibility. You are given the power if you're trying to use a pointer. So if you do some problem there, then the compiler is not going to help you in any way. All right, and your code will your program will start functioning weirdly. So that's why your return type is sort of free now. So what you can use it to indicate is like for error reporting. So say you're doing a swap function, and if you have a return type called bool. This basically indicates that I want to return whether the swap function has happened successfully or not. So if it is all completed successfully, you can return a true value, else you can return a false. So you can do some check over there in the swap function just to make sure that the code has been executed successfully. All right. For good programming practices, what we do is we try to keep the return values as bool. But this is not possible for every single function, only for the ones that is possible. All right. Yep. So Neris, does that mean that you can use it to return different values in a task-based async method with a return type? So when you say return, Neris, can you just unmute yourself? Yeah. So when you say return different values, does that mean that you can use it to return different values? So do not use the term return because it's slightly misleading. You're talking about changing the values in the function, right? Using arguments. Are you talking about that? Yeah. So you can use it to change the different values in any sort of function, whether it is as long as with a return type task. So if you have a return type task, I'm not sure what that function does. Um, hmm. Okay. Okay. Yeah, that this is to be the best way. Yeah. So if you have a return type task, you can also update that. There's no problem with that. You can do the you can just update the values in the arguments. All right. Yeah. Okay. So everybody else is okay with references? So that's almost the end of the slides, I believe. Yeah. So that's about references. So the only thing is about references. Reference is an alias name to any variable that you want to create an alias name for. And the declaration is int ampersand, sorry, the data type ampersand and the name of your reference variable equal to the variable that you want to refer to. All right. So remember, it is absolutely important to indicate which value it is referencing and also clearly give the data type of the variable that you want to refer to. If you don't do that, the compiler will throw you an error. So in some cases, the compiler's errors are helpful so that you don't end up with problems later on. Okay, so that's about references. So are you all okay? So I'll just finish off the next slide as well. We're not even at 10 now. We usually have our break at 10:30. All right. So you're all okay. I'll move on to the next slide then. So yeah, this is about bitwise operators. So it's all dealing with bits. All right. Do you guys remember how many bits makes up 1 byte? I'm waiting for your answer.
Eight.
Anybody remembers? Yeah, what is that?
8.
Yeah, that's right. So 8 bits make up 1 byte. All right. So usually all our data types works in terms of bytes. So your char has 1 byte. Integer is usually in some of the systems has 4 bytes. Then it can be 2 bytes as well. All right. So that depends on your operating system. All right. So that's how all the data types basically works in terms of bytes. Like floating point has 4 bytes, double has 8 bytes, and so on. So we also have the power to work on bitwise stuff. And that's what we'll be seeing here. All right. So these are few bitwise operators that you have to make some changes to your bits. So you've already seen these operators before. This is the bitwise AND operator, the OR operator, XOR. Have you learned about XOR in maths?
Yep.
Okay. All right. So you know how that works. So this is a complement operator, and then we'll be seeing about right shift and left shift operators. So you already know what AND operator is. AND basically gives you a result 1 only if both the operands are of value 1. So if both the values that you want to AND are 1, only then gives you 1. In all of the cases, it gives you 0. So we'll see each one now. Okay. So the way you would use it is, say something like x and y. So x might be some value 12 and y might be another value 13. So if you do 12 and 13, it gets the binary value of 12 and the binary value of y, that is 13, and does a bitwise operation on each and every bit in your value. Okay, so when you have x is equal to 12, the binary equivalent of that is 1100. Yeah, 1100. All right, and y is, since it is 13, it must be 1101. So if you add the two bits, if you add the two x and y, you would do a bit by bit ANDing operation. So that's what is shown in this slide. Okay, so if you do a bitwise AND operation, if both the bits are 1, 1 is placed at the same location, and in all of the cases, you would get a 0. So suppose I'm doing a bitwise operation for these binary bits. So these binary bits indicate some decimal value. Internally, all these decimal values are converted into a binary form, and then the required operation is done. All right. So you have a 1 and 1 in the first one, you get the result as 1. In all the other cases, you would find a 0 there. So 0, 1 is 0, 1, 0, 0, 0, 0, 0. So if you have at least 1 0 in your in the case of your bitwise AND operation, you would end up with a 0. So only in cases where you find 1 and 1, you can see the result as a 1. So the result of these two, the result of the AND operation of these two bits, of these two bit patterns, is 0, 0, 0, 1, 0, 0, 1. All right. I hope you're okay with this. So just want to arrange one below the other and then calculate the bits one by one. What about the bitwise OR operation? In the case of the bitwise OR operation, the bitwise OR would result in a 0 only if both the values are a 0. Okay, so if there is a 1 in at least one of the operations, I mean, in at least one of the values, then the result would be a 1. So you have 1 and 1 here, you end up with 1. You have 0 and 1, so there's a 1 at least in the second one. You end up with a 1. 1, 0, 1. But in the case of 0, 0, since both are zeros, you end up with a 0. So these are the only situations where you would end up with zeros, where you have both the binary bits as zeros. All right, so that is a result of this bitwise OR operation. So remember the difference between the bitwise AND and bitwise OR. What about the XOR? So XOR is represented by this symbol in here. So the XOR gives you value only if either of the bits is 1. All right. If both bits are 1, the zeros, 0. You can see 1 and 1 gives you a 0 here, and a 0 and 0 gives you a 0. In all of the cases where just one of them is a 1, where just one of the evaluated bits is a 1, you would get a 1. So if you have a 0 and a 1, you would end up with a 1. Or if you have a 1 and 0, you would end up with a 1. So that's what's shown here. So you have 0, 1, 1, 1, 0, 1. But in the case of 0, 0, you've got 0. And in the case of 1, 1, you've got 0. All right. XOR operation, all the bits are calculated one by one. And that is represented by this symbol in here. So moving forward, bitwise complement represented by this complement. Complement basically means just complement the bit value. So if you have a 1 there, that becomes a 0. If you have a 0, it becomes a 1. And that's about it. All right. So you can see all of these bits get inverted. So go through each one and you can see everything gets inverted. And that is your bitwise complement, represented by the symbol in here. All right, so I'll just wait for Neera's comment. Do you have some doubts? I heard that you can switch an ASCII character between uppercase and lowercase by flipping a single bit. That depends on the ASCII value, Neris, because if you see the ASCII, like the lowercase a is a value 97, and the uppercase a is a value 65. I'm not sure what their binary representation is, but see if there is. I don't know. I'll need to check that out to see if it is if how many bits we'll need to flip. I cannot tell you for sure at this point. Flipping 32-bit. The difference between what is the difference between A and A? So the difference between the two is like 32. Yeah, so that seems to be logical. Yeah, that's right. Yeah, what he says seems to be logical. Yeah, that's right. Okay. Okay, yeah, so you can experiment around with the bits. That's right. Okay. So, yeah, that was a few bit operations that you're already familiar with. Now going to the right shift operator and the left shift operator. So the right shift operator, like the name suggests, is basically just shifting the bit values onto the right side. All right. So if I say something like X right shift Y, which is indicated by your two greater than symbols, you are saying that this X will need to be shifted by Y times, will need to be right shifted by Y times. All right. So for an example, if I say 8 right shift 2, what I'm saying is I want to shift 8 by 2 bits to the right. If I want to clearly see what shifting 2 bits means, I will need to give the binary representation. All right, so 8 is 1000. Shifting it by 2 values to the right is in this manner. So the 1 over here shifts twice to the right side, and the 10 comes to this position. All the other values over there are replaced by zeros. Okay, so your right shifted result looks like 0010, and 0010 in your decimal form would be the value 2. Okay, so that's what right shift means. Just shifting your bits by as many values as that is indicated by the right hand side value. What about left shift? Left shift is just the opposite. So if you say X left shift Y, which is indicated by X and your two left hand side symbols, this means X has to be left shifted by Y times. So if you say F left shift 1, the binary representation of 5 is 0101. And if you left shift by 1, you move the 101 to the left hand side. So that becomes 101, and the empty space is replaced is kept as 0. So you end up with 1010, and that value is 10 in your decimal format. All right. So that is your right shift and left shift. So remember, all these operators work only on binary on your binary forms. Everything works on the binary, but in your left shift, right shift, you're specifically saying
We can't hear you anymore.
Yeah, your microphone died again.
Okay, can you all hear me now?
Yep.
Okay, I don't know why that keeps creating a problem this morning. Okay, so sorry about that. Actually, I have no indication from here other than reading a message that there's a problem with the mic. Okay, so yeah, what was the thing again? Yeah, so Bravo, each open space, yeah, will be filled with a 0. So if you do a right shift operation, if you have your empty space there, that is going to be filled with 0 or your left shift. Okay. So any other doubts with the right shift and left shift? So if you notice what's happening over here, in the case of the right shift operator, when I do like for example 8, I end up with a decimal value 2. So what do you think is happening over here? Since your binary value is basically a base 2, what happens is the same as saying 8 divided by 2 to the power of 2. Yeah, that's right. You divide 2 times, or you can say 2 to the power of 2. 2 to the power of 2 is 4. All right, so 8 divided by 2 gives you the decimal value 2. Whereas in the case of the left shift operator, here you're doing 5 left shift 1. So in the case of this left shift operator, it's the same as saying 5 times 2 to the power 1. So 5 times 2 to the power 1 is 5 times 2, that is equal to 10. So that is another way you could get your left shift and right shift results immediately without actually finding the binary values. So that's what we're talking about over here. So the operation of the right shift operator is equal to dividing by the powers of 2. So this is the same as x right shift y is the same as x divided by 2 to the power of y. And the left shift operator is equal to multiplying by the powers of 2. Okay, so x left shift y is the same as saying x times 2 to the power of y. If you don't remember these rules, just try with some binary values and then you'll remember whether it was the divided by or the multiplied by. So do not get confused by this. All right. So any doubts there? Jacob? Nothing. Okay. All right. So just another last point. So in some of the cases, whenever you do a modulus operation, do you remember what a modulus operation is? This symbol here, what does this mean?
It's the remainder after a division.
That's right, yeah. Yeah, that's the remainder after division. So Hamish, Jacob, Jake, yeah, you've all given the same answer. So this is the remainder after operation. So in some of the cases, you could also find that a remainder of the operation can also be replaced by a bit masking. Okay, that is basically performing an AND operation with another bit pattern. So if I were to do something like a modulus 16, so say the A value was like 43,725, and this is the bit pattern for 43,725. If I was to do a modulus with 16, I would result in the remainder 13. I don't need to get the bit pattern to find the remainder. I just need to divide it and get the remainder, and I would end up with 13. Now, if I were to get the bit pattern and do an AND operation value 15, that is with a bit pattern of 15, I would get the same result, 13. All right. So this is one instance where a modulus operation can be replaced by a bit masking. So if you wanted to find the modulo 16, all you need to do was perform an AND operation of that value of that bit pattern with bit pattern of 15. I know you might think that is pretty complex. It's much easier to find the division. But then the advantage of going for 15 is 15 is basically 11110 zeros. So this basically means the last 4-bit value is the result of that modulus operation. Okay, because if you remember the AND operation gives you a 1 value only when both of them are 1. So on all the remaining bits, it's going to be 0. So in this case, you would end up with 1101, which is basically the same as of the last 4 bits of 43,725, or the last 4 bits of the integer value a. Okay, so a ANDed with 15 will keep the lower 4 bits and set all the upper bits to 0. So for the other modulus operation, you will need to find out, you can find out which is the bit pattern that can be masked with the value in order to get the resultant modulo, in order to get the resultant remainder. In the case of 16, the AND operation can be done with the 15's bit pattern, that is the same as just extracting the last 4 bits of the value that you want to find the remainder of. All right. So this is just an example. Bits can also be used in other finding the modulus operation.
How did you get the value 15? Like, for example, if you wanted to of 13, for example, what value would you use in the AND situation?
So you mean if you do something like a modulo 13?
Yeah, exactly.
Uh, try out 12. See if you can add it with 12 and get the same value or not. Try it out. This is using trial and error.
Right. Okay. So it's
All right.
not
This is just an
entirely
example where we're just showing
Right.
where the modulus operation can be replaced by. So this is one of the example that where a few bits can be used instead of just few bits can be used to get the result instead of basically getting the division, performing the division operation of such a big number and getting the result.
Right. Okay. So it's more of just
Okay.
a demonstration of how the bits interact rather than a different solution to the modulus.
Yeah.
Okay.
So in the case of modulo 13, try out whether uh, 12 works or not.
It
All right.
doesn't seem
In
to.
in many of the in cases where you have the multiples of 2, I think usually the like this this is a 16. So since this is one of the powers of 2, this works.
Right. Okay.
But usually I think in many of the cases, the powers of 2 do work similar to this. For the other cases, we will need to figure out something else. There might be some other bit pattern that we are not aware of.
Okay. All right. Thank you.
Okay. All right. Yeah. So Neris, what is 0f? Yeah. So 0. This is the hexadecimal form of representing f. So 0x. If you remember in the in the week 2 or something, we had shown the different ways of representing hexadecimal and binary forms. So hexadecimal is as decimal as 0x, the binary is 0b, and so on. Okay, so f is your 1111. All right. So any other doubts at this point? So I think the bit patterns were sort of okay, except for maybe this slide. This is just an example. All right. In the case of 16, if you just add it with 15, you would get the result there. Adding it with 15 is basically keeping the lower 4 bits, because 15 is is like the easiest way, because since all of them are ones. All right. So yeah, that comes to the end of the bitwise operators. Any doubts? Hamish, Neris, I can see you guys are typing. What are the benefits of using bitwise operations? Um, well, you have since your compiler basically converts every single value that you give, like an integer value or character value, into a bitwise into bit patterns. If you directly give it bits, you're basically speeding up the operation. There's no conversion involved internally. Of course, when we type out our code, it's not feasible to write in terms of bit patterns, but it's good to understand what happens internally. And if you basically use your bit patterns to make things easier, then it'll be much faster for the compiler too, because there doesn't need to be a conversion code in there. Right. So does an efficiency, yeah. And so readability wise, this is not readable at all. That's true. But efficiency wise, yeah, it'll make it much faster. Okay, so it's a good, I mean, at least it's important for you to understand how bit patterns work. So Hamish, we can't use and as there is no bit in 00. Okay. Probably not and. See, I'm not saying for sure that is an and operation. That could be some other operation. All right. So if you were doing a modulo 13, I don't know, I'll need to experiment around that and see what it's not for I mean, it's not always an and operation. It could be anything else also. Maybe anything else of the bit pattern of the bit operations. Yeah, it could be an or an XOR also. That depends. I mean, it's like all of your maths discoveries. So maybe you can find out another formula for bitwise operations, and then that will be under your name. All right. Okay. So any other doubts, Jacob? I'll just wait for what you're typing. Anything there, Jacob? It was.
No,
Or
I was just
anybody
writing
else?
down
Any
my
doubts?
thoughts. Don't worry.
Oh, okay. All right. Okay. So that was that was your 2 lectures for today. And I've already shared your exercises. So just take a short break, maybe like around till 10:55. All right. And then, so take a break till 10:55. And then we'll get back and do a little bit of lecture of day 10, since we're missing next week's lecture and I don't want it to all clog up. Okay. It's important that I take a little bit of the lecture that we're missing out next week, because I will be giving out your final project summative the week after, in week 11. Okay. So let's just get all the a few of the lectures get done. I mean, by then I don't want everything else to clog up. Fine. All right. So see you after the break then, and message me for any problems in between. So I'll just go mute. Why are we missing a lecture 10? Because you have a public holiday the next week. All right. It is Anzac Day next week.